Hello, this is week 15's lecture for Chem 1A. So first, start off with something that we have already learned about. It's bonding and anti-bonding. This is where you meet the little funny shapes from what you know already from hybridization. Bonding you get from adding, and anti-bonding you get from subtracting the bonds. And they are typically the lone pairs. That's what they represent. Here, right under that, you get the d orbitals, and you can see how when you add them, because the d orbitals are like little clovers. So when you add them, the top two combine and the bottom two combine to get like little hot dog bun type of shape. But at the very top, they have like little like just pairs of like separated clovers. That's what they look like. Then the p orbitals would form pi shapes. Here, like right above that other image, you see how when they are like anti-bonding, like at the very top there's the C atoms and constructive overlap, but over at the bottom is destructive overlap. Over there you see how it's like a little butterfly shape, and then they combine with the p bonding, because it's like two like p bonds, that's pi. And the top is just like separated butterflies, that's just because they're anti-bonded. At the very top they're bonded, and then at top of that, which is like right over next to the anti-bonding and the bonding and anti-bonding like paragraph, is an image of a carbon with its sp3 hybridization, and then it shows you how they combine to form two carbon or C2. Then we have radicals. This is a molecule with unpaired electrons. They don't follow the octet rules. They are very active because of their unpaired electrons. They are formed at high temperatures or by energetic events and are important, or not all of them, but typically important to the atmospheric chemistry. Then there is molecules with multiple central atoms. The two examples we were given were aromatic and polycyclic aromatic hydrocarbons. So the first one is just there's a rule that they have to be like cyclic and unplanar compounds with delocalized electrons above and below. So typically it means that like they have to form resonance structures. If they can't, they likely is an aromatic structure. And then the polycyclic aromatic hydrocarbons are just like a lot smaller, like crystalline here, C18H12. These can like enter your body because they're just that tiny, and they can mess up your DNA or in the transcription phase. And then the covalent network bonds are both a molecule and a crystal at the same time, or even not the time. But examples of this are diamonds, silicon, gallium, and arsenide. At the bottom here we have examples of diamonds. I think graphite and silicon. They're both the first pair are made of the same shape or same molecule, but they just have different structures. Here is a close picture of graphite. If you've ever looked at your pencil, you can see how it's like little, like an interesting shape to it. That's why it falls apart so easily. And then formed of carbon, like I explained before, there was graphite and carbon. There are two examples. So they form into localized double bonds, like in graphite. And at high pressures, it's where diamonds form. And then eventually return back to coal, but not for a long time. And these are also called the allotropes of carbon. Then we have crystalline and amorphous. They are composed of the same material, but their properties are different. They melt at different points, and examples of this are quartz and glass, like graphite and coal. They will form depending on their structure, which is either ordered or unordered. And here's a picture of quartz right there at the bottom, in comparison to glass, which you can just look at a window and see, observe. Then we have London dispersion forces and van der Waals forces. These are the really weak ones. They are instantaneous simple forces that have occur in one atom and then have a chain-like reaction in the other atoms. The boiling points increase as one mass increases, and the boiling point goes down as surface area shape decreases. And then the dipole forces are a lot stronger and typically are likely polar. Water is example, they have hydrogen bonds, but that's an example of dipole forces. And here are hydrogen bonds, which is again a type of dipole force and has polarity. It connects with a hydrogen atom that has already in the molecule, and then to one N, O, or F. The best example of this is water, obviously, because H2O, or H connects to O. But here is another example of Na connecting with oxygen. And then ion dipole forces. This is water that can form attracted ion dipole interactions and lets you dissolve ions in water. Such as an example. From strongest to weakest is ionic, valent polar, which is like dipole, hydrogen, and then van der Waals. And over here we have like a little image of the ion dipole forces and like more an explanation of what it does with its cation and anions and the two molecules in the front. Anyway, that's about it. Good luck. Take care.